The topic of the video is symmetry and conservation laws. In the Heisenberg's picture for an operator A, the equation of motion is d by dt of A is equals to 1 over I h cut into the commutator of A with h plus dou A by dou t as equation number 1. Next, we try to explain that the conservation of linear momentum is actually a consequence of spatial displacement symmetry of the system. If a system is symmetric with respect to the spatial displacement, meaning that when you actually transform x to x plus dx, then the Hamiltonian of the system should be same. That means if you take the partial derivative of h with respect to x, then it should be equals to 0. And if you multiply minus ih cut to this equation on both sides, we get minus ih cut into dou by dou x into h equals to 0, but px is defined as minus ih cut into dou by dou x. So we can write px into h is equals to 0 as equation number 2. And if you take the Hermitian adjoints on both sides, that means if you take daggers on both sides, we get h dagger into p dagger on left hand side and 0 on the right hand side. Since these h and p are actually Hermitian operators, h dagger is equals to h and p dagger is equals to p, so we get h into px is equals to 0 as equation number 3. And if you kind of subtract equation number 3 from equation number 2, then we get px into h is equals to h into px. That means the commutator of px with h is equals to 0. And since this operator px is minus ih cut into dou by dou x, and it does not have any explicit time dependence, we can actually write down dou px by dou t is equals to 0. So the equation number 1 for the case of operator A being just px operator can be written as dpx by dt is equals to 1 over ih cut into commutator of px with h and dou px by dou t. But just now we have seen that this commutator and also the partial, they are zeros. So we get dpx by dt is equals to 0. That means your px is a constant. So therefore we can state that the conservation of linear momentum is actually a consequence of spatial displacement symmetry of the system. And next we try to actually explain that the conservation of energy of a system is a consequence of time displacement symmetry of the system. If a system is symmetric under time displacement, that means when t goes to t plus dt, then Hamiltonian h remains the same. Then we can write down dou h by dou t is equals to 0. And the equation number 1 for the case of when a is equals to h is written as d by dt of h is equals to 1 over ih cut into the commutator of h with itself and dou h by dou t. Since commutator of an operator with itself is 0 and also dou h by dou t is 0 here, we can write the right hand side as 0. That means h is a constant. Since h is the total energy of the system, we can even say that the conservation of total energy of a system is a consequence of time displacement symmetry of the system. Next in the discussion is explanation for the conservation of angular momentum, which is a consequence of rotational symmetry. If a system is symmetric under rotational transformation, that means when phi goes to phi plus d phi, then Hamiltonian of the system does not change. That means the partial derivative of h with respect to phi will be 0. And if you multiply that equation by minus ih cut on both sides, we get minus ih cut into dou by dou phi of h is equals to 0. But minus ih cut into dou by dou phi is also your Lz operator. I mean the z component of angular momentum. And then so we can write the above equation as Lz into h is equals to 0 and call it as equation number 4. And if you take daggers on both sides of the above equation, then Lz h whole dagger is equals to 0 which will be h dagger into lz dagger is equals to 0. Since h and lz are Hermitian operators, we can even write h dagger is equals to h and lz dagger is equals to lz. So we get equation number 5. And if we subtract equation number 5 from equation number 4, we can write down lz into h minus h into lz is equals to 0, or the commutator of lz with h is equals to 0. And since lz does not have any explicit time dependence, dou lz by dou t is also 0. And the equation number 1, for the case of operator A being lz operator, which will be for d by dt of lz is equals to 1 over ih cut into the commutator of lz with h, and partial derivative of lz with respect to t, will be giving you 0 in the right hand side. That means lz is a constant. So we can say that the conservation of angular momentum is actually a consequence of rotational symmetry of the system. That's it in this video. Thanks for watching.